electricity. So that's what we're going to be doing. We're going to be taking ionic compounds and using electricity to drive a non-spontaneous reaction into a separation of the two substances. So, for example, sodium chloride, boom, I have sodium and chlorine in the end. It's non-spontaneous, but hey, we can give it a little nudge. All right, some of the things we have to know for this are just some identities. So let's talk about that. We have to, first of all, determine the number of electrons needed to reduce or oxidize whatever species we're dealing with. For example, if I wanted to reduce zinc 2+, I would need 2 moles of electrons per every mole of zinc. Don't know why that's capitalized. If I were working with aluminum, 3 moles of electrons would be required to reduce 1 mole of aluminum. And I know that just from the charge. For chlorine, it's going to require 2 moles of electrons per mole of Cl2 because each of the chlorides can give away 1 electron. So that's why there's 2 moles there. And we can always look at our reduction potential sheet to determine that as well, because it will show you the numbers of electrons that are required to get the product we're looking for, or vice versa. We can read it backwards for oxidation as well. So in physics, people talk about moving charge, coulombs of electricity. So a coulomb is a unit of charge. Electrons also have a charge, but in chemistry we always talk about the moles of electrons. So we need to be able to link the two, and we do that through the use of Faraday's constant. That is a capital. Let's give you some credit there. Faraday's constant. A Faraday is 96,500 coulombs per every mole of electrons. Or another way to look at that Faraday's constant is that it equates the fact that 1 mole of electrons has a charge of 96,500 coulombs. So we're going to be talking about coulombs when we're talking about the electricity, but we're going to be talking about electrons when we're talking about the chemistry. So we need that link. That's important right there. Saw this on The Simpsons once. Mr. Burns asked Smithers to write a check for a Faraday's worth of money, so 96,485. I thought that was funny. Another part we have to consider is time. So you may have heard of amperage. Amperage is the number of coulombs that are traveling per second through a circuit. So if I have a 3 amp current, amps is abbreviation for amperage, a 3 amp current would be transferring 3 coulombs of electricity every second. Now how much is 3 coulombs of electricity? Well, it's actually charge. We'd have to go back and look at the 96,500 coulombs is equivalent to 1 mole of electrons. We've got a conversion factor there. So amps are the number of coulombs per second. All right, so here's the first question. What mass of copper can be reduced from a copper chloride solution in 5 minutes with a 2.60 amp current? So the first thing we need to do is just talk about the reduction of copper. We know that copper has an oxidation state here of +2. So it would need 2 moles of electrons to get 1 mole of copper. So to speed things up, I've just shown the math here. So the first thing I did was take 5 minutes and converted that to seconds. So I have 300 seconds. We already said the 2 moles of copper are going to require 1 mole of copper is going to require 2 moles of electrons. Now, the working stoichiometry here. We have seconds as our input, but we know it's a 2.6 amp current. So I set the 2.6 coulombs per second as my amperage. That way my seconds cancel. Now I'm talking about coulombs. I'm in physics world. I changed the coulombs to moles of electrons. So 1 mole of electron is equal to 96,500 coulombs of charge. My coulombs now cancel. I'm dealing with a mole of electrons. I know from my equation, a mole of copper is going to require 2 moles of electrons. And from the periodic table, molar mass, 63.5 grams of copper is 1 mole of copper. Therefore, 5 minutes at a 2.60 amp current would give me 0.0257 grams of copper being reduced. Now here's a problem where we're going to work a little backwards. So if 0.246 grams of chlorine is oxidized from an NaCl solution in 5,025 seconds, what was the amperage of the current? So first of all, I want to go back and look at our reaction. And chlorine right here as an oxidizing, so we were going to read it right to left, every mole of chlorine requires 2 moles of electrons. So I'm going to take that equation. Obviously, I've written it correctly in the right direction now, left to right. But this is the oxidation of the chloride ion into chlorine. I'm going to start with the mass this time, 2.46 grams of chlorine. Then I can use the molar mass to convert to moles. And from my equation here, I know that it's going to require 2 moles of electrons for every mole of chlorine. That's what I'm done with the chemistry. I move myself into the physics by saying, okay, a mole of electrons is 96,500 coulombs, and boom, now I know how many coulombs of charge must be moved. I also know the time, this many seconds. The number of coulombs per the number of seconds is the amperage. So coulombs per second, 0.133 amps. All right, so there's just a couple new ideas that we can talk about. Coulombs of charge being 96,500 coulombs per mole of electrons. If we have access to our reduction tables, we can see how many moles of electrons are required to accomplish the goal we're looking for. That gives us a ratio. And we also can look at amperage as the number of coulombs per time. So a couple new conversion factors, but it still works out as our stoichiometry friend. All right, thank you very much.